Okay, so now that everybody who's here anyway has their test back, um, I forgot to mention last on Monday, a few common mistakes. One other common mistake that I observed, but sort of was pointed out on people's papers individually, was if you have a um, solution such as this that has complex roots, so constant like e to the alpha t cosine beta t plus c2 e to the alpha t sine beta t. And if you were given initial conditions to satisfy, so you had to take the derivative of this. A lot of people messed up taking a derivative. Right here, you have to use a chain rule when you're differentiating that part of it and multiply by beta. The second last problem in particular, actually no, it's problem 5. The second constant is it's 5/9. So a lot of people got 5/3 because they forgot there's a cosine 3t or sine 3t and didn't multiply by 3. So it happened enough that I want to point that out as a common thing to avoid in the future. Not that it costs many points, but there's so many other opportunities not to lose points. Okay, so what I'm going to do today is the test featured the simplest possible kind of problem involving a spring. And I talked a little bit about upper spring problems back when I covered that section, but I'm going to go back to that for problem set 12, which has 4 problems from a textbook in all. And one of them similar to one of the tests and 3 others that are more advanced. And that's going to be due on Monday. And then what's going to happen is, because we're getting close to the end, as I get into the next chapter, instead of giving a roughly 1 problem set per section, I'm going to give 1 Whopper problem set on the whole chapter, chapter 4 that's coming up. So it's a bigger set, so it has more problems on it. But that means you also have longer to do it. So we're going to finish. So next week, it's still a pretty quick chapter. I'm going to just take next week because we don't have class Friday. So I'll take next week covering that, and then you'll have 1 week after that to do that problem set. And then there'll be 1 chapter left, chapter 6 on Laplace transforms. We may not get through the whole thing, get through as much as possible. I'm not aware of any other class in the undergraduate curriculum that makes use of Laplace transforms, so it's not something where you're setting yourself up for suffering later on if something is not covered. But so then there'll be 1 last problem set on that. So that means there's going to be well, actually, no, that one's split in 2. So there'll be 15 problem sets in all, but I will drop the lowest one. And as a reminder, let's see, 60, 65. Homework counts for 30% of a grade altogether. And then there's this test is 20%, so is the other one. Final is 25%. Attendance is 5%.
You said homework was 30%?
Well, okay, you had the 2 together. Yeah. Okay. All right. Yes. Oh, right. Okay. 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 And if you have any questions about the grading of a test, okay. All right. Then you can just ask me afterwards. So the general form of equation for modeling the motion of an object attached to a spring is mu double prime plus gamma u prime plus k u is equal to big F of t. And on the test, you had a watered down version of this where gamma was 0 and big F was 0. But now we're going to bring back both of these. And so m refers to mass. Gamma is your damping constants. And then k is your spring constant. And big F of t is any external force. Now, I'm going to give us a little chart, because what happens with these problems is, problems described in words, you're not given all of this equation. You have to come up with it from the information that's given. So I'm going to make a chart of units for various quantities that are involved in this problem, whether you're dealing with English units or metric. So, for instance, if we're dealing with the mass, little m, so for instance, metric that would be grams or kilograms. I'll just write one of the units in each case, and then English units that works out to be pounds seconds squared per foot. Or does anyone know the informal term for that? Yes, it's a slug. Okay. Of course, now it makes you think of, since I used to live in California, University of California, Santa Cruz, their team name are the banana slugs. Okay. Anyway. And then we have, constant g that comes up for gravity. And then we have, like meters per second squared here, and then the gravity constants in each case, 32 versus 9.8. The constant K, the spring constant, is pounds per foot in English units versus kilograms per second squared. And then weight. So often the weight of the object is given in English units, and that's just plain old pounds. But for metric, it would be kilogram meters per second squared, which is also known as a what? What? Newton. Okay. Or it might be like in the using grams, centimeters, seconds. So it'd be like 10 to the minus fifth meters. And finally, the damping constant, gamma, is pounds seconds per foot in English units, and then it's kilograms per second in metric, or that'd be the same as Newton seconds per meter. Now, what I would suggest, so a couple tips for the homework before I go into some examples for my notes. This is homework 12. As a reminder, this happens down when you turn in homework, please write the problem set number on the assignment. And most of you are doing that, but I want to make sure everybody does. Because sometimes I'm grading going through more than one stack, and I like to separate them. Because of the test, yes, I know I'm behind on grading homework, so expect an avalanche of graded homework to be coming at you on Monday. Okay, so some tips for this problem set, for 4 exercises from the textbook. 2 of the problems involve damping and 2 don't. So for one thing is, I would suggest using meters. If a problem is in metric, All right, so I'm not suggesting it's already in English, you can stick with those units, but not centimeters. So if any quantities are given in centimeters, just go ahead and convert everything to meters. And for problems that involve damping, the constant is not given to you directly. They're not saying gamma equals this. What they're saying is that the damping force, if they give you that amount of force, like in newtons for instance, when the velocity of the object is such and such. So what you're going to do is you're going to divide force by the given velocity. And so those two quantities are given. And then you'll get your damping constant. All right. Okay. Everything else in the problems, and because either they give you the mass already, or they give you the weight, and from that you can just divide by gravity constant to get the mass. And then keep in mind K is equal to the weight divided by the equilibrium length, and that is already given in the problem. And then a verbal description of initial conditions, like is the object pulled down to give a value initial displacement? Is there an initial velocity? There's one problem that actually has both of those things. So you can have two non-zero initial conditions. Okay. So what I'll do now is, I didn't get a chance to do this before, is go over some examples that involve either damping or an external force. All right. So we have an object with a mass of 20 grams, and by itself it stretches the spring 5 centimeters, and like I said before, take my advice, convert to meters, 0.05 meters. So here's your spring, and that's your equilibrium length L. And we have now in this example, the damping constant is given. So that'd be 9 seconds per centimeters, which is at least consistent with the dyne seconds per centimeter. Okay. Let's see. And actually, but I want to stay with meters. So we have well, except actually, I don't need to convert because it's a subtle point, but dyne is 10 to the minus fifth newtons, which includes a unit of length in it. So in fact, there's already a implicit centimeters in this unit here, so the units of length actually cancel out. So, it's consistent with the units given over here. So, so I don't actually need to change that number to reflect that I'm doing everything in meters. So, while it has other dimensions in it, as far as length is concerned, it's dimensionless. Okay. Now, other parts of the problem statement, it is pulled down, I'll draw it, pulled down additional 2 centimeters, and then it's released. So then what is the displacement at any time t? Okay, now, the fact that it's pulled down an additional 2 centimeters and released, what does that say about the initial conditions?
U of 0 is 0.02.
Yeah, 0.02 meters, and then what about,
It's 0.
yeah, because we don't impose an initial velocity on it, we just let it go, and whatever it does, it does. Okay, so, and there's no mention of any external force, so we're not going to bother with that. So we have mu double prime plus gamma u prime plus k u is equal to 0. So m is 20, gamma is 400, and then k is equal to mg over L. So we fill in the mass, 20 grams, times the gravity constant, meters per second squared, 9.8. I saw some people test use 9.81, but I'm going to be relatively lazy. And then we have divided by the equilibrium length, 0.05 meters, and we get this nice large number of 3,920. Grams per second squared. So we have 3920, u is 0. And I'm sticking with grams because this also has an implicit grams in it. Okay, so the units for that is gram centimeters per second squared. Okay, so questions about where the equation comes from before we look at solving it. So the things to actually figure out, as opposed to what's given, are getting k from the other information that's given, and then figure out the initial conditions from a statement that is pulled down 2 centimeters and released. Okay, so now you solve this just like you would solve any given equations we've seen in this chapter, your characteristic equation. So we have 20 lambda squared plus 400 lambda plus 3920 is 0. So you're going to have to whip out your quadratic formula for that one. And I'll just cut to the chase here that your roots, lambda 1 and 2, they turn out to be complex. So we get minus 10 plus or minus, so let's simplify somewhat, 4 square root of 6 I. Okay. So with those being the roots, then what is the general form of a solution? And we have some constants times what?
E raised to the negative 10 cosine of
10,
10t
yeah, we need a t.
cosine
Yep.
of 8t.
4 square root of 6.
This.
Oh,
Yeah, here's the imaginary part.
Okay, 4 square root of 6.
Yeah.
T
Okay, and then what?
plus c2 plus
To
c2
the negative 10.
e raised to the negative 10t sine of 4
Yeah.
square root of 6t.
Yeah. Okay. All right. So now, okay. So question about where the solution comes from before we deal with initial conditions. Okay. So then we can just go ahead and compute. So for instance, u of 0. Whoops. What is u of 0? Yeah, it's just going to be C1. Everything else is going to go away because cosine of 0 is 1, sine of 0 is 0. And therefore, it must be 0.02. Okay. And as for C2, Okay. Oh, that's weird. Okay. Yeah. I goofed in notes that I went back to centimeters. Okay, but 0.02 meters, and then what we need to do is to differentiate this to get u prime of 0. What's interesting here is we have to use product rule here, but two of those terms involve a sign, and that's going to go away when you plug in t equals 0. We really care about the terms that involve cosine. So u prime of 0 is going to turn out to be the term from here that gives you a cosine, which means the cosine has to be undifferentiated, the exponential needs to be differentiated. So you get minus 10 C1. I'm pointing this out because it's a pattern that always comes up in these kinds of problems when you have these complex roots. So whatever constant you have in front of the exponential, u prime of 0 will always have that constant times C1. And then over here, you want a term arising from product rule that involves a cosine, which means the exponential is undifferentiated, the cosine is the sine is differentiated. So you're going to get plus C2, and when you differentiate this, what constant factor is going to be introduced?
4 square root of 6.
4 square root of 6, the one that some people forgot in the test. Okay. And that has to be 0 in this case because of the initial condition here. Okay, so now unfortunately the value that I have in my notes is going to be wrong because I messed up on units. But so you can plug in your value of C1 in here to go ahead and get C2. So we have, all right, so minus 0.2 plus 4 square root of 6 C2 is equal to 0. So C2 is equal to 0.2 over 4 square root of 6. Okay. And now, so now we can put that back in, and we have our solution. And no, I'm not going to rationalize that fraction. Okay. Now, so any questions about getting the solution itself before we look at the other pieces? Now, the quasi-frequency, because when there's no damping, there's just a uniform frequency. So the quasi-frequency is given by mu, which is, it comes from the imaginary part of the root. So it's going to be 4 square root of 6. And the formula for it in general is square root of km minus 4 gamma squared, all divided by 2m. So that just comes from the discriminant from a quadratic formula that's used to get the roots. And we negate it because we have complex roots. But what's interesting is, if I were to try to put this under one radical sign, the whole fraction underneath it, so I'd be putting, oh wait, there needs to be, sorry, I put the 4 in the wrong place. Okay. So I put this under radical sign, I'm going to get 4m squared in the denominator. So that's going to give me square root of k over m minus, and then we have gamma over 2, the whole thing squared. Now, can anyone tell me what is the significance of square root of just k over m? Forget it, ignoring the gamma. Where did that come up before?
That was the frequency without the damping.
Yeah, so the undamped case, that's a frequency. So and it makes sense that if we let this damping constant go to 0, then we're back to that case. So what you should find, and then actually at least one of the homework problems asks about this, to compute the quasi-frequency, and then what is the ratio of a quasi-frequency to the undamped frequency? And what happens is, if the damping constant is small, then that ratio should be roughly 1. Okay. And then you can figure out the quasi-period. So the period is 2 pi over omega naught for the undamped case. So it's 2 pi over mu for the quasi-period. And then you can figure out the kind of an amplitude that now for the undamped case, you know the amplitude is square root of sum of squares of the constants. But when it's damping involved, what's happening is, because of the exponential, it's oscillating less and less over time, and eventually settling to a steady state. So that needs to be multiplied by the exponential that you have in your solution. So if you were to graph this, and plus or minus, what you would find is that the displacement is going between those two curves. So it behaves.
Is the E under the square root?
No, it's not.
Okay.
So it behaves something like that, eventually settling down to rest. As opposed to the undamped case, where the solution says it will literally oscillate forever. Not so realistic. Okay. So any questions about these quantities? And it all depends on what roots you get. Here we get complex roots, there's some oscillation. On the other hand, if the damping constant is large enough, you're going to get real roots. And what will happen is there's so much damping that there's no oscillation whatsoever. That it just quickly settles down to rest in a uniform way. It's not bouncing around. Now, the rest of the time, I'm going to take a look at case of an external force. Some interesting things happen there. Okay, so once you've handled the kind of problem that we just seen, or the undamped case from a test, the damped case from over there, without an external force, but now we go ahead and have an external force. What are you supposed to do to solve that kind of problem? What method do you need to use? Yeah, undetermined coefficients or variation of parameters. Generally, you can use either one. Again, it depends on the function that you have for the force, but the coefficients are all constant. There's a reading question about that. Okay. I just have a natural preference for variation of parameters. So that's what I'm going to look at here. So what's happening is, even if you're not pulling your object down, even if you are not imposing additional velocity, because there's an external force, something is still going to happen. So what I'm going to do is go back to the undamped case and get an idea, for at least for a particular kind of force, what the solution is going to look like. So I'm going to let big F of t be some force F, constant F naught, times cosine omega t. So there's a periodic force being applied to the object. So the force is oscillating over time between plus and minus F naught. Okay. Now, so recall from before, I just came up on a test, that your solution is your homogeneous solution plus your, what do you call it? Particular solution. Okay, and when there's no damping, we know what the form of a homogeneous solution is. So we have some constant A times cosine omega naught t plus another constant sine omega naught t. And omega naught is square root of k over m from your equation with the damping term being ignored. And then for your particular solution, we have a form, W1 of t cosine omega naught t. So that's like my U1 plus W2 of t sine omega naught t. So that's my U2 of t. And then I can use variation of parameters like you did on the test to figure out W1 and W2. All right. So what happens is you can figure out the Wronskian of U1 and U2. The Wronskian of cosine omega naught t and sine omega naught t. And I won't bore you with the computation of that, but it turns out to work out nicely. You just get omega naught. So this you have a nice simple denominator in the integrals that you're going to have to evaluate. So now your integrals will involve your U1 and U2, your Wronskian, and then your right-hand side, your big F of t. Okay. So for instance, W2 is going to be minus the integral of your external force times U1 over your Wronskian. So I'll fill in the pieces. Actually, in this case, considering how I wrote to define the big F of t, there's a little something I'm missing here. If you look back at the equation, before you used to go to work on an equation like this to solve it, like using the ordered variation parameters or undetermined coefficients, what's one of the very first things you're supposed to do to that equation to get it in like the right standard form? Divide by m. Yeah, so I need an m in its denominator because by dividing, my external force is actually F of t over m. Okay. All right, so but now I have two constants I can pull out, so 1 over m omega naught, and then I'll fill in what we have here. So we have, that's not what I wanted. Thanks for pointing it out, everybody. Yeah. Okay, so all right. So we have well, F naught. I can also pull out. That's a constant. So I have cosine omega t, and then we have sine omega naught t dt. Okay. So now we have to integrate something like that, and that's a bit of a pain. I don't suppose anyone, well, who knows, depending on who your Cal 2 instructor was, this might not have even come up. Actually, I think in normally in this department, it doesn't come up. So I don't suppose anybody would know what to do. Omega naught are constants, and for the time being, I'm going to assume that they are not equal. There's a way to rewrite, because you can't really integrate that as it's written. You need to write it in a different form.
Integration by part.
What?
Do you use integration by part?
Fortunately, no. And this is a trig identity issue, not so much a integration technique issue. What?
You sign A and cosine B and divide it by 1 over 2 or multiply by 1.
Oh, you're thinking of like a half angle.
Double.
That's a special case of what we really need. What we actually need is called a product to sum identity. Okay, and that says in this case we have cosine. Cosine of AT sine of BT turns out to be 1/2, and we get sine of A plus B times T plus sine of A minus B T. Okay. Yeah. So now we're going to have different constants like omega plus or minus omega naught in here. But now because we have a sum instead of a product, these terms can be integrated individually. I'm not going to go through all the details here, but it's all written down in the notes. What you get is actually pretty ugly. So you get f over 2m omega naught. And then we have a plus now because the integral of sine is going to be minus cosine. And so what we get is, after we put over a common denominator, omega naught minus omega, cosine omega naught plus omega t plus omega naught plus omega cosine of omega naught minus omega t, all over omega naught squared minus omega squared. So that's why it was necessary to assume that omega and omega naught are not equal, so we don't divide by 0. If it were equal, in that case, you could, in this case, the integration is actually a lot easier. You can perform a substitution. Or in the other integral, we're going to have, for W2, we're going to have cosine and cosine, so you could use a half angle formula for that case. So W2, in this omega, not equal omega naught case, has to work out in a similar way. So that gets pretty ugly. Then you've got to multiply by U1 and U2, so you get something extra ugly that miraculously condenses. And what you get in the end for your particular solution is f naught over m, omega naught squared minus omega squared cosine omega t. So what's interesting is the particular solution turned out to be nothing more than a multiple of your external force. So you're just dividing by omega naught squared minus omega squared, and still periodic. So then you can add that onto your homogeneous solution, usually to get your general solution. And okay, so the general solution turns out to be, well, actually, no, that's boring. I'm going to add that onto the homogeneous solution. But now, I'm going to pose some initial conditions. Initial conditions that are 0. So in other words, we do nothing to this object at the outset. We don't pull it down. We don't impose initial velocity on it. But we do have this external force. So we're still going to get a non-zero solution. And what happens is, as a result, you get the constants a and b over there. B turns out to be 0, a turns out to be minus f naught over m, omega naught squared minus omega squared. And now you can put everything together, your homogeneous solution plus your particular solution turns out to be this, the same scaling factor times the piece from the homogeneous solution, actually, apart from a particular solution, cosine omega t, minus the piece from a homogeneous solution, cosine omega naught t. Now, but the way it's written doesn't really tell you very much about the behavior until you use the opposite of what was used for the integration. Instead of a product to sum identity, use a sum to product identity. And so you can write this difference of cosines as this product of sines. I get a factor of 2 up top, and I have sine omega naught minus omega t over 2 sine omega naught plus omega over 2 t. So this is the solution in the end, where you only have the external force at work. And so as far as the behavior of this solution over time, let's suppose that my frequency from your external force, omega, is approximately equal to omega naught. So then what we have here is the kind of oscillation that you expect from undamped motion just from this factor. But what you have is an amplitude that varies over time. So the amplitude is going to be everything else in the solution. Actually, absolute value of all that. And then the absolute value of this part here, sine omega naught minus omega t over 2. Where the over 2 is including what you're taking the sine of. Now this is, since omega naught and omega are close to each other, that part is almost 0. But the point is, there's an amplitude that varies over time. So the motion of the object exhibits what's called a beat. Like when you have two tuning forks of nearly similar frequencies that are excited at the same time. So that's the behavior that you see in that case. But all along, we've assumed that omega naught is not equal to omega. But more interesting behavior happens if omega naught equals omega. What happens in this case is for your W2, the integral is f over f naught over m omega naught, integral of cosine squared omega naught t. Well, cosine squared omega naught t is equal to, by half angle identity, 1 plus cosine 2 omega naught t all over 2. So the key is when you integrate for 1/2, the integral of 1/2 is going to be what? No, not t squared, but integral of a constant is, yeah, t over 2. So you get a t over 2 term in here. So all told, you get f naught over m omega naught, t over 2 plus some additional terms over 2 omega naught. Okay. So what ends up happening is your particular solution, in this case, turns out to be F naught over 2m omega naught t sine omega naught t. So, what happens to the amplitude? Because the sine omega naught t part, that's the oscillation for the undamped case you come to expect. But look at what's multiplying it. What happens to that as time increases? Yeah, it's gonna. Yeah, as Jeremy did, like that. Yes, it's gonna grow over time. So you're gonna have something like that. Love to see that happen physically, but unfortunately, everything I did from the outset assumed it was undamped. Realistically, we should have some damping in there that would hopefully offset that before your object goes completely out of control and you have an infinitely long spring. Okay, and I'm out of time. So we'll get into higher order equations starting on Monday.